All right, buckle up, everybody, because we are going deep today, like way down to the center of an atom deep.
Ooh, sounds intense.
Oh, it is.
Yeah.
It is. We're taking a deep dive into the nucleus today.
Awesome.
Yeah. So we're looking at left205.pdf. Looks like it's a chapter from a physics textbook all about nuclei. And I gotta say, I'm already geeking out over here.
Oh, yeah. What's got your eye?
Well, they kick things off with this wild analogy. Imagine an atom is the size of, say, a football stadium.
Okay, I'm picturing it. Big atom stadium.
Right. And the nucleus. Well, that would be like a tiny little marble sitting right there on the 50-yard line.
Wow, that's tiny.
Right. But here's the kicker. That tiny marble holds almost all of the atom's mass, like practically all of it.
That's mind-blowing when you think about it. All that mass crammed into such a small space. That density is one of the things that makes the nucleus so fascinating, I think.
Totally agree. And that's what's so cool about this source. It jumps right into explaining how scientists even measure something that incredibly small.
I can imagine it's not like they can just pull out a tiny ruler.
Not quite. They've got this super clever system called the atomic mass unit, or U for short.
Okay, you got it.
And it's all based on taking 112th of the mass of a carbon-12 atom. Like, that's our standard.
Makes sense. Need a reference point. But I remember from chemistry class that atomic masses aren't always neat and tidy whole numbers.
You're so right. So how does that work then if everything's built from these, like, basic units?
Well, think about chlorine, for instance.
Oh, okay, chlorine.
It's got an atomic mass of 35.46 U.
35.46, so not a whole number.
All right. And that's where the idea of isotopes comes in.
Ah, isotopes, okay.
So you can have atoms of the same element, like chlorine, with the same number of protons. That's what makes it chlorine, right?
Right.
But they have different numbers of neutrons.
Okay, so like different versions of chlorine.
Yeah, exactly. So you've got chlorine 35, which is 18 neutrons, and then there's chlorine 37 with 20 neutrons.
Ah, okay, see.
And so that atomic mass you see on the periodic table, that 35.46, it's actually an average.
An average?
Yeah. Weighted by how much of each isotope exists out there in the world.
So it's like if you had a big bag of candies,
Okay, I like where you're going with this.
some are chocolate, some are gummies, whatever, the overall weight depends on how many of each type you've got.
Perfect analogy. So we've got protons, we've got these different isotopes, but how did scientists even figure out that neutrons exist in the first place?
Right. They seem so elusive.
It's a really cool story of scientific detective work, actually. See, at first they knew about protons, positively charged particles,
Right.
but they were stumped by these mass differences they saw in isotopes, especially when they looked at hydrogen's heavier buddies, deuterium and tritium.
Hydrogen's got siblings.
It does, and they're a bit heavier. So something else had to be going on in there besides just the protons. And that's where physicist James Chadwick comes in.
Okay, what did Chadwick do?
Well, back in 1932, he was doing some experiments bombarding beryllium with these things called alpha particles. And he noticed something interesting. These neutral particles were being emitted, and they had roughly the same mass as a proton.
Neutral particles with the mass of a proton. Sounds like he was onto something.
He was. And that, my friend, is how the neutron was discovered.
So basically, Chadwick figured out a new fundamental particle was hiding out in the nucleus by, like, playing subatomic billiards.
Yeah. Pretty amazing, right?
Okay.
But it makes you wonder, if neutrons are all cozy and stable inside the nucleus, what happens to them when they're not in there?
That's a great question. Do they just, like, wander off?
Not quite. See, on their own, neutrons are actually kind of unstable.
Really?
Yeah, they have a half-life of about 10 minutes.
So they don't last very long on their own.
Nope. They decay into a proton, an electron, and an antineutrino.
A whole particle party. But what keeps them from decaying inside the nucleus?
It's all thanks to that strong nuclear force that's holding everything together in there. It basically stabilizes them. So inside the nucleus, they're team players. Outside, they're a little more chaotic.
That's pretty wild. Okay, so we know the nucleus is tiny, it's dense, it's made of protons and neutrons, but how on earth did scientists actually measure the size of something so incredibly small?
It all goes back to one of the most famous experiments in physics, Rutherford's gold foil experiment.
Oh yeah, I remember learning about that. Something about shooting particles at gold.
Exactly. So in the early 1900s, Rutherford was firing these things called alpha particles at a thin sheet of gold.
Okay.
And he was watching what happened to them. And what he found was that most of the alpha particles just sailed right through the gold foil.
Like it wasn't even there.
Pretty much.
Yeah.
But here's the key. A few of them bounced back, like way back, at sharp angles.
Interesting.
Right. So that led him to this incredible insight
What was that?
that the atom is mostly empty space. And at its center, there's this tiny, positively charged nucleus.
So it's like if you took a fence and attached a few marbles to it,
Okay, I like this. Go on.
and then you started throwing tennis balls at it.
Right.
Most of them would just fly through. But every once in a while, you'd hit a marble and the ball would go ricocheting off in a crazy direction.
That's a great way to visualize it.
Yeah.
So that's how they figured out the atom was mostly empty space with a dense nucleus. But to actually measure the size of that nucleus, they needed more powerful tools.
Makes sense. Can't measure something tiny with a giant yardstick.
Right. So they turned to even higher energy particles.
Yeah.
Essentially shrinking their measuring stick to the subatomic level.
Wow. So what did they find out about the nucleus's dimensions? Is it like a perfect little sphere?
Well, they discovered this super interesting relationship. It's between the nucleus's radius, we'll call that R, and its mass number, which is the total number of protons and neutrons. We'll call that A.
Okay, R for radius, A for mass number. Got it.
The radius is actually proportional to the cube root of the mass number.
Cube root. Getting a little mathy here.
It's a cool relationship. They came up with a formula for it. R equals R0 times A to the 13 power.
So what is R0 in that equation?
R0. It's a constant. About 1.2 femtometers.
Femtometers, remind me how small those are again.
Super small. 1/quadrillionth of a meter.
Wow, that's almost unfathomably tiny. But this equation, this R equals R0 times A to the 13 power, what's it actually telling us about how the nucleus is structured?
It reveals something really fascinating. The density of nuclear matter. It's pretty much constant across all the different elements. So it doesn't matter if you're talking about a light element like helium with a mass number of 4, or a heavy one like uranium with a mass number of 238, their nuclei have roughly the same density.
So whether it's light or heavy, the nucleus packs all those protons and neutrons together just as tightly. That's a level of consistency we just don't see in the everyday world.
It's true. It suggests the nucleus behaves almost like a tiny little drop of incredibly dense liquid, all held together by forces far stronger than anything we experience on a human scale.
It's incredible to think about. We've talked about size, density, but what about the energy involved in all of this? I know our source dives into Einstein's famous equation E equals mc squared and this concept of binding energy.
It's a crucial part of understanding the nucleus. So Einstein's equation tells us that mass and energy are basically two sides of the same coin. They can be converted into each other. And this plays out in a really interesting way inside the nucleus.
Okay, I'm listening.
If you could add up the masses of all the individual protons and neutrons in a nucleus, you'd think it would equal the total mass of the nucleus, right?
Makes sense to me.
But it doesn't. It turns out the total mass of those individual parts is actually a tiny bit greater than the mass of the nucleus itself.
Wait, so the whole is less massive than the sum of its parts? How is that even possible?
It's because some of that mass has been converted into energy, and that energy is what's holding the nucleus together. We call it binding energy.
So, like, the energy cost of assembling the nucleus gets stored as binding energy, which then shows up as a tiny bit of missing mass.
Exactly. And the scales involved here are just massive compared to, say, the energies involved in chemical reactions. We're talking mega electron volts or MeV. That's millions of times greater.
It's like comparing a firecracker to the sun, energy-wise.
It really is. Even converting just 1 gram of matter entirely into energy would release a mind-boggling amount of energy, something like 9 times 10 to the 13th joules. That's enough to power a city for a while.
That puts it into perspective. Okay, so we've got this tiny, dense nucleus held together by this huge amount of binding energy. But with all those positively charged protons crammed in there, why doesn't the nucleus just fly apart? I mean, like, charges repel.
It's a great question. And it leads us to one of the most powerful forces in the universe, the strong nuclear force.
Okay, strong nuclear force sounds intense.
Oh, it is. First of all, incredibly strong.
Yeah.
Much stronger than the electromagnetic force that makes those protons want to repel each other.
So it overrides that repulsion.
It does. But there's a catch. It only works over extremely short distances, like a few femtometers, those tiny units we talked about earlier. That's why we don't experience this force in our daily lives.
Oh, it's super strong, but super short range.
Exactly. And here's the other amazing thing. It doesn't care about electric charge. It acts the same between protons and neutrons, or even between a proton and a neutron.
So this force is just like, I'm going to bind these nucleons together no matter what.
Exactly. It's the glue that makes the nucleus possible.
It's incredible how something so small can have such a profound impact on the nature of matter. And it makes me wonder what happens when this delicate balance of forces gets disrupted. Our source mentions this phenomenon called radioactivity.
Ah, yes, radioactivity. That's where things get really interesting.
It sounds like we're about to open a whole new can of worms.
We are, and we'll dive into that in part 2 of our deep dive. Welcome back, everyone. So before we jump into the whole radioactivity thing, I think it's worth mentioning that the discovery of radioactivity itself was kind of a fluke.
Oh, really? Like an accident?
Yeah, pretty much. Back in 1896, there was this physicist, Henri Becquerel.
Okay, Becquerel, I've heard the name.
So he was studying uranium salts and noticed that they were like fogging up these photographic plates he had, even when they were wrapped in black paper.
So something was getting through that paper.
Exactly. It was like they were emitting some kind of invisible rays that could penetrate stuff.
That's kind of spooky when you think about it.
Right. And it really shook things up in the physics world. Becquerel's discovery led to this whole new understanding of the atom. Scientists realized that some nuclei, they're not actually stable,
Unstable.
meaning they can change spontaneously. And in that process, they release energy. And that's what we call radioactivity.
So it's like some nuclei are just too hot to handle and they need to cool down by releasing some energy.
That's a great way to put it. And there are a few different ways they do that. We call them types of radioactive decay.
Okay, so what are the options? How does a nucleus shed that extra energy?
Well, there are 3 main types. The first one is alpha decay. In alpha decay, the nucleus basically kicks out a little chunk of itself called an alpha particle.
A chunk? Like what?
It's basically a helium nucleus.
Helium, like the stuff in balloons.
Yep, exactly. 2 protons and 2 neutrons all bound together.
Wow, so it's like the nucleus is giving birth to a tiny helium atom. Does that change what the original atom is?
It does. When a nucleus goes through alpha decay, it loses 2 protons.
You're right, because of the alpha particle.
So its atomic number goes down by 2. Poof, it's a different element. A classic example is uranium-238. It decays into thorium-234 by spitting out one of those alpha particles.
Okay, so alpha decay is like a nuclear makeover. What about the other types?
Next up, we've got beta decay. This one's a bit more bizarre.
Oh, how so?
Well, in beta decay, the nucleus throws out an electron, or sometimes a positron, which is the electron's antimatter twin.
Antimatter. Now we're getting into Star Trek territory. Hold on, is antimatter even real?
It is, though we don't see it much in our everyday lives, thankfully. Think of it like this antimatter is like a mirror image of regular matter. Same mass, but opposite charge.
Okay, I think I'm following. So a positron is like an electron, but positive.
Bingo.
But hold on, if the nucleus is made of protons and neutrons, how does it suddenly decide to shoot out an electron or a positron? Where are those even coming from?
That stumped scientists for a while, too. Remember how we said neutrons are unstable outside the nucleus?
Yeah, they decay.
Well, similar things can happen inside the nucleus, too. In one type of beta decay, a neutron transforms into a proton, and that process releases an electron and a super tiny particle called an antineutrino.
Okay, so it's like a proton-neutron switcheroo.
Right. It shows how even these seemingly basic particles can change their identity.
What about the other type, with the positron?
That one's a bit more complex. It involves something called the weak force, which is another one of those fundamental forces of nature.
So many forces to keep track of. All right, what's the third type of decay then? You said there were 3.
Right. Last but not least, we have gamma decay. This one's all about pure energy release.
Okay, how so?
The nucleus gets rid of some excess energy by sending out high-energy photons. We call those gamma rays.
Gamma rays. I know those can be dangerous.
They can be. But they're also incredibly useful.
Oh, really?
Yeah, they're used in medical imaging, cancer treatment, all sorts of things.
I guess it's like a lot of things in science. There's the potential for good and bad.
Exactly. It's all about how we understand and use that knowledge.
Makes sense. So we've got these 3 types of radioactive decay, alpha, beta, and gamma. But how does this all tie back to that binding energy we were talking about earlier?
It's all connected. Remember that binding energy curve, that hump-like shape?
Yeah, I think I remember it.
Well, that curve basically tells us that both splitting heavy nuclei, like uranium, and fusing light nuclei, like hydrogen, can actually lead to more tightly bound configurations.
And what does that mean in terms of energy?
It means energy gets released. Think of it like a ball rolling down a hill. It naturally wants to go to a lower energy state.
Okay, so the nucleus is always trying to chill out, energy-wise.
Exactly. For big, heavy nuclei like uranium, splitting up is the way to go. We call that fission. And that's what powers nuclear reactors and, unfortunately, atomic bombs, too. The uranium nucleus breaks apart, releases some neutrons, and boom, huge energy release.
And that's why fission is both a potential energy source but also kind of scary, because that energy release is just so
You
massive.
got it. It's millions of times more energy than a typical chemical reaction.
Yeah.
So, yeah, we got to be careful with that one.
Well, sure. What about fusing those lighter nuclei? What happens there?
Well, when you combine those light nuclei, we call that fusion.
Mm.
And that's actually what powers the stars.
No way. So our sun is basically a giant fusion reactor.
It is. It's constantly fusing hydrogen into helium. And that releases an incredible amount of energy, which is what makes the sun shine.
It's wild to think that all that energy we feel from the sun comes from these tiny nuclear reactions happening millions of miles away.
It really is. And that's why scientists are so interested in figuring out how to control fusion here on Earth.
Yeah, fusion power seems like it could be a real game changer. Clean, safe, basically limitless energy. But if it's so powerful, why haven't we cracked it yet?
It's a tough nut to crack. The main challenge is getting those positively charged nuclei close enough together so that the strong force can take over.
But they want to repel each other, right? Like trying to force the same poles of a magnet together.
Exactly. And to overcome that repulsion, you need crazy high temperatures and pressures, like sun-level conditions.
And I'm guessing that's not so easy to do here on Earth.
Not exactly. Scientists are working on it, though, using all sorts of cool technology like powerful magnets and lasers to try and control the process. It's a huge engineering challenge.
So controlled fusion is like one of those ultimate quests in science.
It is. It's pushing the limits of our understanding and technology. But if we can do it, the potential is huge.
Definitely something worth striving for. Okay, so we've gone from nuclear structure to radioactivity, and now to the mind-blowing world of nuclear energy. Before we wrap up, I noticed our source has this little exercise where they compare and contrast chemical and nuclear reactions.
Sounds like a good way to recap some key differences.
It does. So the first thing they ask about is balancing nuclear equations. Like in chemistry, where we had to make sure the same number of atoms are on both sides of the reaction. Does that apply to nuclear reactions too?
It's a great question, and it highlights a key difference. In chemical equations, we're concerned with conserving atoms. But in nuclear equations, it's all about conserving nucleons,
Yeah.
the protons and neutrons.
So it's not about the identity of a specific element, but more about making sure the total number of protons and neutrons stays the same?
That's it. Chemical reactions, they rearrange atoms. Nuclear reactions, they can actually transform elements completely.
Okay, that makes sense. The next question digs into how mass and energy get converted in a nuclear reaction. But we just said that the number of protons and neutrons stays the same. So where does the mass change come from?
That's where binding energy comes back into the picture. Remember how the mass of a nucleus is a tiny bit less than the mass of all its protons and neutrons added up?
Yeah, that was weird.
Right. Well, that missing mass is the binding energy. So even if the number of protons and neutrons stays the same in a nuclear reaction, the binding energy can change. And if the products of the reaction end up being more tightly bound, then energy gets released and some mass is converted into energy, according to Einstein's famous equation.
So it's like the number of pieces stays the same, but the strength of the glue holding them together can affect the overall mass. That's crazy.
It is. It's all about how mass and energy are fundamentally linked.
And the last question in this little exercise really blew my mind. It basically says that even chemical reactions have tiny changes in mass. But I always thought those were just about rearranging electrons, no mass changes involved.
Well, the mass changes in chemical reactions are ridiculously small compared to nuclear reactions. But technically, they do happen, because chemical reactions involve changes in the energy stored in chemical bonds. And those energy changes, however small, mean tiny changes in mass, according to EMC2.
So even burning a log in a fireplace involves a tiny bit of mass turning into energy. That's wild.
It is. It shows that Einstein's equation applies everywhere. Mass and energy are connected in everything.
Mind blown. I feel like we've gone on quite the nuclear adventure today. Where do we even go from here? Wow, we've really gone deep on this journey into the nucleus. It's amazing to think that something so tiny can have such a huge impact. We're talking the secrets of stars, the power of nuclear energy, even the basic building blocks of matter.
It really highlights how interconnected everything is, from the tiniest particles to the whole vast universe. It's all governed by the same basic laws.
And this deep dive into left205.pdf has really driven that point home. We started with this picture of the nucleus as this little dense speck at the heart of an atom. But the more we've explored, the more complexity we've uncovered.
And we've only just scratched the surface.
Yeah.
There are still so many mysteries about the nucleus. Like, how do all those protons and neutrons, how do their individual movements lead to the overall behavior of the nucleus as a whole?
And what about the shape of different nuclei? What makes them stable or unstable?
Right. And then there are the more practical questions, like how to achieve control fusion power. We talked about the challenges, but is anyone actually making progress?
Yeah, what's going on in that field? It seems like that's the holy grail of energy.
Researchers are working on a bunch of different approaches. Some are using super strong magnets to contain the super hot plasma you need for fusion. Others are using lasers to heat and compress the fuel.
It sounds so futuristic.
It is, but it's a really tough challenge.
Well, I'm glad people are working on it. If we could figure out fusion, it would be a huge step forward for humanity.
No doubt. And it's not just about energy either. Understanding the nucleus has implications for so many fields: medicine, archaeology, even material science.
It's like a ripple effect. The more we understand the fundamentals of matter, the more we learn about everything around us.
Exactly. It just shows how important scientific exploration is and how our curiosity can lead to amazing breakthroughs.
I'm walking away from this deep dive feeling a real sense of awe. It's incredible how this tiny thing, the nucleus, can be a microcosm of the whole universe.
It's like a stage where the fundamental forces of nature are playing out this intricate, awe-inspiring dance.
And who knows what we'll discover next as we keep exploring. Maybe the nucleus holds the key to new forms of energy or understanding the origin of the universe. Maybe we'll even learn how to manipulate matter at the most basic level.
The possibilities are mind-boggling. And that's what's so exciting about science. It's a never-ending journey of discovery, pushing the boundaries of what we know and what we can imagine.
I don't know about you, but I'm feeling inspired to keep questioning, keep exploring, and keep diving deep. Because the universe is full of wonder and there's always more to uncover. Thanks for joining us on this incredible journey.
Absolutely. Until next time.